Hello, my name is Saif, and today I will walk you through my team's proposal on how to achieve automotive weight reduction with alternative materials and manufacturing techniques. This presentation was put together by myself, my teammates Sarang, Kaushal, and Esteban. A quick overview of the presentation. We'll be going through the background and motivation of our research, understand the problem statement by going over our gap, and how we're going to address the problem, and then we're going to analyze our design and technical application and understand what the data tells us. And from there, we'll be looking at the results of our conclusion and future work. The world is seeing aggressive policies pushing for a phase down in CO2 emissions, and changes to motor vehicle regulations are imminent. With the rise of electric vehicles and cleaner propulsion systems, all manufacturers are being pushed to make their vehicle lineups more efficient to both remain competitive in the marketplace and to comply with new regulations. An example of such aggressive regulatory frameworks is the new European Clean Mobility Standards, which aims to force car manufacturers to reduce the average CO2 emissions of their fleets. Now, since the last targets were met ahead of schedule, the new targets have been set to be significantly more aggressive. Some manufacturers have started taking steps towards compliance by outright removing their most inefficient engines from their lineups. One clear example of this is Mercedes-Benz getting rid of their V12 biturbo engines. Additionally, European regulators are offering financial and timeline incentives for manufacturers who put forth quote-unquote significant efforts towards phase down. Now, although these incentives help, putting forth qualifying initiatives represents significant capital and time commitments, and some manufacturers do not have the capacity to pivot their entire business model. Now, the key to compliance with these new challenging regulations is to manufacture more efficient vehicles. When looking at it from a quick win perspective, what are the best ways to reduce emissions and to make a car more fuel efficient is by either making smaller cars, smaller engines, and smaller and more efficient engines, or outright lighter cars. Now, developing new cars and new engines or redesigning existing cars and engines to be more efficient and smaller is more expensive and takes a lot of time. So from our perspective, we'll be looking into making cars lighter, because from a basic physics standpoint, lighter vehicles require less energy to overcome inertia and move about. And a reduction in 10% of a car's unsprung weight directly translates into a 6 to 10% boost in mileage. And better mileage is a synonym to lower emissions. Weight reduction seems to be the answer to these difficult challenges. But how do we reduce weight? If you look at the highest echelons of competitive motorsport, you find an entire industry at the forefront of research and development of more weight efficient materials in an effort to boost performance and win competitions. So why not take those materials and put them in the mainstream vehicle? Current carbon fiber manufacturing methods, specifically pre-impregnated composite fibers manufacturing and resin transfer molding methods, are too cost intensive, too wasteful, and very labor intensive. And this presents a serious challenge to even consider implementation in a fast-paced modular assembly line. This presents us with a gap. How can we, introduce these methods to the mainstream automotive industries and the mass producers? And how can they implement cost-effective alternatives to higher-end, lower-weight materials such as carbon fiber? Here we refer to these higher-end materials as those that have a proven performance advantage when compared to traditional ones, but due to their cost are just too expensive to implement in mass-produced vehicles. Our team is proposing the use of a three-pronged approach to overcome the barriers associated with the use of carbon fiber in vehicles. These approaches include substitution, alternate manufacturing methods, and additives. Currently, all three of these methods are used in modern automobile manufacturing to some extent. However, they are usually reserved for higher end applications such as sports cars and spaceships. We intend on pursuing the idea that a combination of all three of these applications would yield a benefit large enough to justify the use of carbon fiber in mainstream automobiles. Additionally, given that carbon fiber weighs less than traditionally used aluminum and steel, vehicle owners would also see a benefit in the form of extended range or efficiency as a result of reduced weight. Manufacturers could look into the possibility of changing the manufacturing process in which carbon fiber-based parts are made. And that's basically our first proposal. The industry today relies on prepreg and resin transfer molding. These processes are suited towards low volume production as they are manual, sequential production processes that generate waste byproduct. The mass market automotive industry could overcome this limitation by switching to a pultrusion-based manufacturing process. Pultrusion is designed for repetitive, high-volume manufacturing of parts, which is an ideal use case for mass-market vehicles that have manufacturing runs in large volumes as opposed to high-performance vehicles. One caveat of pultrusion is that it is only applicable for constant cross-section parts, therefore limiting the flexibility of its geometry as denoted by the figure in this slide. This generally limits the applicable use cases of pultrusion as vehicles are often composed of many irregular shaped parts. However, the combination of pultrusion with overmolding can yield complex part structures where utilizing a lightweight core that is manufactured through pultrusion. This would enable manufacturers to take advantage of low-cost pultrusion manufacturing while retaining desired part geometry and flexibility. From our second proposal, which is the material substitution, and which is the case of substituting long carbon fiber with short carbon fiber. Here our objective is to reduce the weight of automotive components in an affordable manner for use in mass market vehicles. We propose substituting long carbon fiber with short carbon fiber. SCF, short carbon fiber, can be safely used for non-structural parts, including engine covers and interior trims. In addition, data suggests that it might be potentially used even in structural applications because the specific strength of 40% weight percentage composite of SCF and nylon 6.6 is only about 6% lower than an identical composite using LCFs. One drawback, however, is that the notched impact strength is about 45% lower. However, this should not present a real problem because failure by impact can be split into two separate processes. We have crack formation and then crack propagation. However, real-life parts would not ideally contain cracks or notches, thereby making these parameters a little bit irrelevant. Manufacturers should be able to safely use a vastly cheaper SCF safely in the presence of a stringent quality control program. This, however, would require detailed research and development study by automakers. Glass fiber is increasingly being used to manufacture high-volume automotive components to reduce weight and was easier than carbon fiber to adopt. And this takes us to our third proposal, which is using additives and fillers, this is the case of partially substituting carbon fibers with glass fibers. One method to decrease weight without excessive cost increase is to reinforce glass fiber composites with carbon fiber along the main load paths. These hybrid composite laminates are made by weaving an epoxy resin matrix with carbon and glass fibers. It has been experimentally determined that a 50% carbon fiber reinforced laminate, where carbon fibers are on the exterior, provides the best flexural stress properties. The graph above shows that glass fiber is less stiff, more flexible than carbon fiber, which means that a glass fiber component would have a higher ultimate breaking point than an identical carbon fiber component. This implies that glass fiber has a higher strength to weight ratio and is essentially a tougher material. Carbon fiber, on the other hand, is more brittle and less capable of enduring certain types of stress due to its higher rigidity. Thus, a case could be made that a glass fiber carbon fiber hybrid composite would impart increased toughness to the component, allowing the vehicle to absorb more energy in a collision, while reducing raw material costs by partly substituting carbon fiber with the more economical glass fiber. As we move forward, we will be performing various analyses of our manufacturing techniques. Since our goals here are to decrease costs and waste and increase overall strength, our team will be testing against these three design criteria specifically. In the event of testing and benchmarking our design, we imagine the process will have an iterative nature to it, where we have to go over the manufacturing technique several times to reach the best possible outcome. Once again, as a result of these regulatory pressures and severe penalties imposed by government agencies, automobile manufacturers have had to find new ways to adopt emission reduction technology. As a result, manufacturers are looking for new and innovative methods to improve their vehicles' efficiency by decreasing their weight. The challenge that lies here is for mainstream automotive producers to implement cost-effective methods to carbon fiber and mass production. Our team put forth three proposals and changes to make to the manufacturing process. This includes substitution, alternate manufacturing methods, and the use of additives. Thank you for listening into our presentation. We hope it was informative and helpful.